Okay, so let's refer back to the rate law. I have it written up here. Again, you guys don't need to copy it down because you guys already have it in your notes. But like we said before, the rate law is for a generic equation. If we have something like this, basically we get the rate law by taking the compounds, the reactants, multiplying their concentrations to the power of m and n and multiplying by the rate constant. Okay, so hopefully that's review. Okay, so this is another example right here. So if we were looking at this reaction, we just take the two reactants, ammonium and nitrite, and then we find their concentrations and then multiply by K and then to the power of, usually their coefficients, but not always. Okay, so far so good? All right. Now, we're going to be talking about something called reaction orders. So I want you guys to just write that term down, reaction order. Okay. I guess this is the part that you guys can write down. But the reaction order is the sum of the orders with respect to each reactant. Okay. Basically, what that means, if you want to just have that in plain English, the reaction order is equal to the m plus the n. So the exponents, you add the exponents together, and that gives you your reaction order. Okay, so easy example is this one right here is exponent 1, 1 plus 1. So this is a second order reaction. Yes.
What does that mean?
We'll get to that in a second. Yeah, it basically lets us know how the reaction actually takes place, like what happens mechanically. Yeah, so we'll talk about what a second order is, a first order is, a third order, whatever, what all that means in a second. But for now, we just need to be able to find the reaction order. Yeah. Not the charge. We'll get to that in a second. I'll explain how we determine it. Yeah. Yes. I'm actually not familiar with what you're referring to, so maybe. Oh yeah, we're gonna be talking about that. Yeah. M and N is basically the exponent for the reactant concentrations, right? And it tells us basically how in the reaction these reactants are consumed, how they're used in the reaction. And then to the power of 1 to the power of 2 just tells us how they're used. And we'll get to that in a second, guys. I know you guys are trying to figure out what this means, but at least for now, any questions on how to find reaction order? That part's pretty easy, right? Okay, you just add M and N. Okay, so the key thing that I want to highlight about reaction orders is that last time we said that the exponents are the same as the coefficients, right? Okay, for the most part, that's always true, okay? Except when they tell you otherwise. So a lot of times you can just think of it as the same as the coefficients, but the rate law is always determined experimentally. So just because I give you this general law saying usually M and N are equal to the coefficients doesn't mean it's always like that, okay? The rate law is always determined experimentally. So I'm going to give you guys some examples here to take a look at. Now, if you guys take a look at the first example, you guys see the coefficient is 2, right? So we would assume that for the rate law, it'd be to the second power, right? But if you guys notice, it's not, okay? So that's my way of kind of showing you it's not always going to be like that. So don't always assume that just because the coefficient is 2, the power is going to be to the power of 2, okay? It's not going to always be like that. Yeah. Yeah, they would give it to you. Okay. Here's another example right here. If you guys take a look at the coefficients here, it's 1 and 1, right? And so for one of the compounds, the exponent is 1. But for the other one, it's half. Okay, so that's my way, again, showing you sometimes one of them is going to depend on the coefficient and the other one is not going to depend on the coefficient. Okay, and then the last one, it's 1 and 1, and you get 1 and 1 as you would expect. Yeah.
And if it's not given to us,
then you can usually assume that it's going to be the coefficients. Yeah. Okay, so yeah, I know it's kind of confusing because I'm giving you a rule that doesn't always work. But yeah, just be aware of that. Yes. Yeah, it's because it's determined experimentally. So when they do experiments, that's what they found it to be. Yeah. Okay. So just keep in mind, most reaction orders are going to be 0, 1, or 2. Sometimes you'll get half, sometimes you'll get 3. I've never seen a problem where you go get like 4 or 5. So if your number for your rate order is getting too high, something's wrong. Okay, so you might want to check that out. Okay, but just keep in mind, you can even have a fractional, so 1 and 1/2, or sometimes even a negative rate law or rate order. Okay. I know that you guys must be very confused right now about this, but like I said, this is why I hate this unit. Okay. All right, so you guys don't need to copy this table down. This is just kind of our way of just bringing everything together. So let's say this is the rate law right here. Let's just take, I'm going to zoom in. Let's take a look at this first row. You guys can see that the exponent for x is 1. The exponent for y is 1. So this rate law is going to have an order of 2. Okay, it's going to be second order. Make sense? This one right here, it's to the power of 2 and to the power of 1. 2 plus 1 is 3. And then 1 plus 2 is 3. So that's how you determine rate order. Okay, so just keep that in mind. At least for now, just remember that you're going to be just adding the exponents to get the order. All right. So far, so good? Okay, basically, at least for now, just know add m and n, and that gives you the reaction order. Okay, now the reason why these are determined experimentally is because the exponents in a rate law determine how the rate is affected. Okay, so basically, if we go back to the original rate law, so the one that we had here, this one right here, let me just copy it down so we have it as reference. Rate is equal to K, and then NH4 plus, and then NO3 minus, okay? Or NO2 minus. Okay. So basically, because the rate at which ammonium reacts with nitrite depends on this guy raised to the first power, if you double the rate, okay, so the rate doubles when NH4 plus doubles. So if you double this number, so let's say this number was 1, and then you turn it into 2, that means the entire rate will double because it's 2 to the power of 1. Okay, and we're talking very abstractly with numbers. Okay, but if you turn this from 1 to 2, that means the rate will also double. Okay, and then if you triple it, then it will triple, so on and so forth. And then same thing here. Okay, and the reason why is because both of them are to the power of 1. Okay, yes.
So you're saying like triple the rate and then also triple.
Yeah, you got to triple the concentration of one of them to triple the rate.
So wait, what's triple?
Yeah, one of them. So let's do a quick example. Let me just rewrite it, and then we'll put numbers in so you guys can visualize this. Okay. So NH4 plus. Okay, and NO2 minus. Okay. Let's say, for example, that the concentration. Let's just do easy numbers. Okay, 1 and 1. Okay. So if we just do 1 and 1 for these rates, 1 second. Okay. So that means that if the concentration of ammonium and nitrite is 1, that means the rate is just going to be 1, right? 1K. Make sense? K times 1 is 1K. So far, so good? Okay, let's double one of them. Okay, let's double ammonium. If we double ammonium, it's going to be 2. Okay, this guy is still going to be 1, right? Okay, what is going to be the new value of the rate? 2K. So if you double one of them, it doubles the rate. Make sense?
It doesn't double.
What do you mean? It does double because if you go from 1 to 2, you double the concentration of one of them. You go from 1 to 2. You doubled the rate. No, it's independent of each other. Because if you look at the math, right? So let me show you what happens when you double both of them, okay? So let's say we double both of them from the original values. If we double both of them, we go to 2 and 2, right? What's the new rate if you double both of them? 4. So if you double both of them, you quadruple the rate. Because each of them is working independently, and if you double one of them, it doubles. If you double the other one, it doubles again. So you quadruple it if you double both. It's just the way the math and the exponents work out. Okay. I know this must be very confusing and abstract. Yes.
More than 2.
Yeah, so you can have multiple reactants as well. So that'll change up the numbers even more. But usually they'll give you 2 reactants to work with. Yeah. Okay. Does that make sense, guys? Always just keep in mind, this is the equation you're working with. And when in doubt, just plug in numbers into that equation. That'll allow you to find out the pattern. Okay. Okay, now I'm going to describe this again with the example that we just had. Okay, so this is the reaction that we had, and we can see that if you double the concentration, so the rule that you guys don't need to write this down, but if we double the concentration, that means you double the rate. Okay, and this is for when the rate order is second, when the exponents are 1. Okay, so when the rate order is 2. Okay, so this is when the rate order is, sorry, I'm gonna rewrite this so that's nicer. So when the exponents are 1, if you double the concentration, you're gonna double the rate. Okay, so far so good? And that's what this is showing us right here. Okay, but let's change up the equation a little bit. Okay, if we change the rate law. Okay, so if we change the rate law so that let's say that we have a squared right there. Okay, just trying to get you guys familiar with the algebra. Okay, so if you square it, you're still going to get 1K for your rate, right? Okay, but let's say you double the concentration of this guy right here, okay? So instead of 1, you turn it into 2. So it's going to be 2 squared and 1. What's going to be the new rate? Yeah, it's going to be 4K. Because you're multiplying. It's okay. So I know this is very confusing because you got to really look just at the equation. Okay, so if we double the concentration of the guy that's getting squared, it's going to quadruple the rate, right? Because 2 to the power of 2 and then times 1. So just keep in mind that if depending on what the exponents are, that's going to change how the rate changes. So if your exponent equals 2, and then you double the concentration, you're going to 4x the rate. Okay, so it's all going to depend on the exponents of your, or the exponent for your reactant. And then you can probably kind of tell what's going to happen if, let's say, we put it to the power of 3. Okay, then that's going to change it even more. That's going to be times 8. Okay, so as the exponents rise, the rate is also going to rise exponentially. Okay, yes. No, just be comfortable using this equation, because trying to memorize all these things, it's just too much space in your brain to take up. I would say as long as you're comfortable with working with that algebra, then you should be okay. Yeah. So you don't need to copy this down. You don't need to memorize it. Just know that this is the pattern that comes out of this. Okay. All right. Any questions on the algebra? You guys good with that? Okay. I know it's very, very confusing. Like I said, this is why I hate this unit. Sometimes, yeah. I make a lot of mistakes, as you guys know. Okay, let's move on. So that's what this is telling us. Okay. So I want you guys to take a look at 11.8 based on the information that we learned. Here we are considering a reaction A plus B produces C. Okay, and this is the rate law. Okay, the rate is equal to K the rate is equal to K times the concentration of A times the concentration of B squared. Okay, for each of these boxes, okay, A is the red ones and B are the purple ones, because I don't want you guys to laugh at blue again. Okay, and I want you guys to rank these mixtures in order of increasing rate of reaction. Okay, so I have the rate law for you guys right here. each of these boxes have a different concentration of red and purple. Okay, I want you guys to find out which one has the highest rate and the lowest rate. Okay. So take a few minutes to do that, and then after that, we'll go over, make sure you guys understand how to use this rate law equation properly, okay? Okay, so if we take a look at box 1, what is the concentration of A? Oh, that's the rate, yeah. So I'll just give you the rates, actually. That's probably better. The rate is 125K for number 1. Everybody got that? Okay, we got 5 and 5. For number 2, the rate will be 63K. Okay, because we got 7 and 3. And then for the last one, we're going to have 147K. All right, so let's rank them in order of the rate of reaction. Which one is the fastest reaction? Okay, yeah, 147. So 3 is the fastest. And then obviously it's going to be 1 and 2. Okay. Okay, so basically what I wanted you guys to identify here, let me just put it right here. So for number 1, you're going to have a ratio of 5 to 5, 5 red to 5 purple, right? And then you get 125. If you get a ratio here of 7 to 3, you're going to get 63. And then if you have a ratio of 3 to 7, you're going to have 147. Now, what I want you guys to notice is that it doesn't matter if we have more of the red ones here. Okay, this is still going to be the slowest reaction because since the exponent is only 1, the red is going to affect the reaction rate the least. Okay, so red affects the reaction rate much less than the blue ones. Okay, so just keep that in mind. That's basically the conclusion that we can draw from this rate law, that depending on the exponent, the order of each concentration, it's going to determine how much it affects the reaction rate. Okay. And obviously, if it's power of 3, it'll affect it even more, so on and so forth. Okay. All right. A little easier to use, or it's not that difficult to use the rate law, right? No problem. Okay. Okie dokes. Let's move on. Okay. So I want you guys to use your noggins a little bit. So I'm going to give you guys some time to try 11.9 on your own. It's a lot of information. There is a table, okay? But this is where the question is right here, okay? So I want you guys to take some time to just go over it. You can work with the person next to you. But I want you guys to get used to seeing these problems and trying it out before I explain anything to you, okay? A lot of info. There's a reaction right here. It's already balanced. You guys don't need to balance it. And I want you guys to use this info right here to determine first the rate law. I want you guys to write the rate law and figure out the rate constant if you can, okay? But if you can get the rate law on your own, I would say that you are in really good shape, okay? So try it out. Try to get at least the rate law. And if you could find the rate constant, that'd be great. I'll give you a hint. Most of it, you're going to be analyzing this table and comparing the trials, okay? So I'll give you guys about 3 minutes to try it out, and then we'll go over it together. Okay, so like I said, you want to compare the trials. We're going to be first comparing trials 1 and 2, okay? So we're going to go through all of the numbers in the trials, and let's see if you guys can notice anything different about them, okay? So my hint was, you're going to compare trials 1 and 2. So for the concentration of NO, is there any change? No change, right? So I'll write NC. If you look at the change in concentration for ozone, O3, is there any change? Okay, what's the change? Yeah, nice. It doubles. Okay. And then if you guys take a look at the change in the product or the rate of the product formation, what's the change? It doubles, exactly. So what this information tells us, I know, right? What this tells us is if you double the O3 concentration, okay, so if you double it, what happens to the rate? It doubles. So what's the exponent for this, for O3? 1, exactly. So we know that the rate is going to equal K times the concentration of NO to, M, we don't know the exponent. And then for O3, We don't know the exponent, but we found out if you double O3, you double the rate. That means this has to be 1. The exponent for O3 has to be 1. Okay. Make sense? Okay. All right. Let's go to the next one. I said you need to compare 3 and 4. So how does it change right here? Doubles. How does it change right here? Yeah, no change. And then how does the rate change? Yeah, double. So what's the exponent for NO? 1. Also 1. Good. So this is your rate law right here. Yeah, Vivian and then Jade. You could, but then it would be a little bit more difficult for you to see the difference between the two of them right here. All right, you wouldn't have a nice clean number to work with. Yeah.
Sorry, how, know that O3 was one?
O3 is 1 because if you look at trials 1 and 2, this is the one that shows the change for O3 concentration, right? It doubles between 1 and 2, and then the rate also doubles. And that's how, so if you double the concentration of O2, the rate doubles, which means that O3 is going to have a concentration of, or exponent of 1.
And why does it not?
Or the concentration is not 1, but the exponent is 1 because remember earlier we said that if you double this number, 2 to the power of 1 is going to be 2, so you're going to put a 2 right there. Yeah, referring back to the old one. What's up?
Why don't we use
NO2 is a product,
Oh,
so it doesn't pertain to the rate law. Mhm.
Okay.
Yes.
well, is it because so like
Yes, you could.
So is it what you were saying? There was something that was started.
Yeah, so in this situation, the coefficients, you could have used them. Yeah, you still need to check because remember the exponents always determined experimentally. So the experimental data is going to trump whatever coefficients there are. Yeah, good observation. Yeah.
so if O3 doubled twice, then it would
So if O3, let's say right here, if you double it and then this went to like times 4, then you would know that this is to the power of 2. Yeah, good observation. So yeah, that's how you can figure out what the exponent values are. Okay.
but not if O3 doubled twice, like the third and fourth trial.
Oh, between here?
Yeah.
So usually you want to just compare 2 data sets, because if you do it right here, it's going to be 1.5, and then this is also going to be a 1.5 difference. And then, yeah, then you would have to simplify the exponents and it gets a little bit trickier. Yeah. Yeah, so I would always recommend look for whole numbers and only go to fractions and decimals for these exponents if you really have to. Yeah, good question though. All right, any other questions? Okay, so based on that, we can calculate the rate constant. Now, the rate constant is very, very easy to find. All you got to do is pick one of these trials and just plug in the numbers, because no matter which one you pick, you are going to get the same rate constant, okay, because it's a constant. Okay, so let's just pick one and plug it into the formula right here. Now, we're going to be solving for K, so we can rearrange our equation. K is going to be equal to the rate divided by the concentration of NO to the power of 1 and the concentration of O3 to the power of 1. Okay, and so all we got to do is plug in the numbers that are given for that trial. Now, again, you could pick trial 1, 2, or 3, or 4. It's going to give you the same constant. The only thing that you need to keep in mind is make sure you get all the numbers from the same trial. Okay, so don't go mixing and matching. So we'll put 0.66 times 10 to the negative 4 on the top. We're going to divide by the concentration of NO in trial 1, which is 1 times 10 to the negative 6. And then the concentration of O3 on the bottom, 3 times 10 to the negative 6. Okay. And I'm going to give you guys a minute to try figuring that out because I know that exponents are really hard to work with on the calculator. So take a second to practice it. I'll give you a minute to plug it in, compare with the person next to you, and see if you can actually get the unit of measurement too, and the final answer. Okay. Take a minute to do that, and then we'll double check, see if you got it right. I don't like where this conversation is going. Exactly, exactly. You guys make me very, very deeply unhappy. All right. So let me give you guys my very unhappy answer. Okay, you're gonna get 2.2 times 10 to the power of 7. Okay, so if you guys, you could go 1, 2, 3, 4, 5, 6, 7. That also works. Just make sure that you have 6 zeros. Okay. Everybody good with that? Okay, let's get the unit of measurement. Now, rate is measured in molarities per second. So I'm gonna write it like this: molarity and then second -1. We know that concentration is measured in molarity, so 2 molarities. Now you're gonna notice that you can cancel out one of the molarities, but you got a molarity on the bottom. So for your unit of measurement, you can do molarity -1, seconds -1. Okay, if you also wanted to do it like this would also work. Either way, it's fine. Just remember, just keep in mind, these are the units of measurement: molarity and seconds on the bottom. Okay. So that's how you would balance out the units of measurement. Alrighty, any questions? Easy peasy? Not really. A bit. It's weird. It's very abstract, yeah. You gotta be very comfortable with your algebra. And then now you gotta use information from a table to do that as well. Okay. Now, I know the units of measurement are very weird for the rate constant. And you can just think of the rate constant as a way that we balance out the units of measurement. And so you guys might notice if there was a 2 right here, your unit of measurement is going to be different, right? Because you'll have another molarity on the bottom. And so you guys can solve it out. But I know some people don't like doing the solving. This is what we just did, the calculating. But if you guys just want to remember it, memorize it, write it down, you guys can. Here is your units of K. If your order, the reaction order is 0, it's going to be a nice one, molarities per second. If the reaction order is 1, it's going to be per second. If the order is 2, this is the one we just did, it's going to be per molarity per second. And if it's 3, it's going to be per molarity squared per second. Okay, it's just the way we balance out the units. It's almost impossible to visualize what this means because it is so abstract, but if you can, great for you. But just keep that in mind. That's how the unit of measurement per reaction order. Yeah. Yeah, so one easy way for there to be 1 is if the rate is just 1 equal to 1 chemical. So let's do my favorite. Okay, and it's just the power of 1. If there's only 1 reactant, that's one way that we can have a reaction order of 1. For us, and this is just talking about a hypothetical reaction. So some reactions have only 1 reactant. They're decomposition reactions. Yeah, where one thing breaks down into multiple, that would be a react. Those are usually the ones that you'll have a reaction order of 1. You can have a reaction order of 0, and we're going to talk about what that means in a second, but I'll kind of tell you right now. A reaction order of 0 basically means that the reactant concentration, so the reactant concentration, it doesn't affect the rate. Okay, so yeah, exactly. The rate is always the same. Yeah. So there's some reaction. It doesn't matter how much you start with, always going to have the same rate. And those are the 0 order reactions. Yeah. Good observation on that.
Like in the very first unit, I don't remember what it was called, but it was like talks about whether a property had to like was dependent on quantity.
Mm-hmm.
Like could we? I don't remember what the actual like words
Mm-hmm.
were, but could those be applied here? Like
yeah. Some reaction. So most of the time reaction rates depend on the quantity, but sometimes it doesn't. Yeah. So yeah, that's a good. I don't remember what that's from unit 1, but if it's there, I believe you.
Yeah, it was
Yeah.
like a random book out, and I don't remember the word,
But yes, yeah, that works. Yeah, that principle applies here. Yeah, sure. I'm gonna go back and look at what that is. All right, guys. So we're gonna practice writing rate laws a little more. I want to give you guys a little bit more practice on identifying these patterns because AP tests, they're gonna love messing with you, giving you a bunch of data, having you identify or to interpret the data and do stuff with it. So this is the same thing. I want you guys to write the rate law and the rate constant for this reaction right here, okay? Take about 5 minutes to do that. Okay, so now one thing I do want to mention before we start these problems is if you guys ever have exponents, I already did it for you here, but it's nice to have everything in the same power. That way it's a lot easier to work with and compare the numbers in front, okay? So let's take a look at trials 1 and 2. As you go from 1 to 2, how does the concentration change? It doubles, right? Okay. And then as it doubles, what happens to the rate? Yeah, quadruples. Okay, so from there, you can already stop and write the rate law, okay? You can write the rate law as K is equal to the concentration of your compound to the power of what? 2, yeah, because 2, and then the rate quadruples, so it'll be 2. And if you really wanted to make sure that you did it correctly, you can check right here too. You would also notice that as the rate or as the concentration doubles, it's going to quadruple right here as well, okay? So even across trials, it's going to change like that, okay? Alrighty, any questions about rate law? Okay, let's go to rate constant. I'm just going to give you guys the value just to save on time. Same thing, you can just pick a trial to work with. But for your K value, you should get 6.73 times 10 to the negative 6. And then since it is second order, it'll be per molarity per second, okay? That's going to be your K value. Something around there. You want me to go over it? No, this every time that you get a new problem for experiment data, you'll get a new chart. Yeah.
Why? I thought it was just like S. There's only one.
That's true, but we have to add the total of the exponents. This is to the power of 2. Is that where you guys all? So yeah, so for your rate law, this is your rate law. Your K value is equal to the rate divided by the concentration. And then it has to be squared. Yeah. The one with the units of measurement?
Yeah.
So if you want to memorize units of measurement, you can, but you can also find it out in every problem because it'll always be the same rate law, right? And then you can do this right here. The rate is always molarities per second. And then right here, it's the concentration is always molarity, right? So it'll be molarity squared, cancel out the molarity. And so you can always figure it out mathematically. And so if you prefer to do that, then you don't need to memorize it. But if you don't want to go through that, then you can memorize it. Yeah, so it's optional. Exactly, exactly. And then Brendan, was that the reason why? Okay, for sure. Cool.
Oh, maybe you said points get taken off.
The unit of measurement, I mean, it depends on what the problem is. I'm going to actually show you. So some of the problems that we're going over in this, that we'll be going over next, some MCQs are dedicated to having you figure out units of measurement. So that would be the whole problem then. If you did it, let's say they asked you the answer on a FRQ, maybe half of that point, half for the value of the number, and half for the unit of measurement. So it really depends on which problem it is. Yeah. Mm-hmm. Yeah. Not necessarily. They might not. Yeah. So I would always recommend changing everything to the same exponent just so it's easier to work with just by looking at the numbers. Because 2.06 times 10 to the negative 11, it's a lot easier to compare the numbers in the front when they're the same. Whereas if the exponents are different, because if it's like to the power of 9, it'll be like 0.0824. If you want to move the decimal to the right, you are going to make the exponent value go, yeah. So you just move the decimal and change the exponent likewise. Yes.
I got 6.7. I got the exponent honestly. But when you put the CH3 CHO on the bottom, don't you like put the exponent?
No.
Yeah.
So plug it in the right way because you need to square it first, and then you got to divide it.
Why did you flip it on the other? Put it on the blind, but it makes
Yeah, I plugged in it the way it is.
it's positive.
Pretty sure I did it. I just plugged it. So yeah, I just plug it in exactly the way I get it. So 1.75 times 10 to the negative 3. And then the top you plug in 2.06 times 10 to the 11. Yeah. 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 It's a good way to think about it. Alrighty. You guys good? All right. So two last things, and then we'll get straight into the practice problems and we'll end the class for that way. Now, don't freak out. Okay, because I know y'all are freaking out right now by looking at this. Okay, let me clarify. You do not need to memorize this, okay? Unless you guys really piss me off or something. If you guys really piss me off, I'm gonna give you this blank chart and you gotta fill it in, but I don't see that really happening. Yeah, no, we ain't doing that. Okay, no. Okay, so this is all the derivations that you can get from the rate law. If you guys want to read more into detail about it in your textbook, you can. But basically, this is all the information that they can use the rate law to test you on. Okay, they can have you look at graphs. They can have you graph a little bit. They can have you write slope formulas using it. So just keep that in mind that they can do stuff like that. So I would look at this section very briefly, but I really want to emphasize the most important thing is to do as many practice problems as possible, because you can sit around and memorize all this stuff, but it's better to just encounter these in practice problems, because then you'll see how we can apply like things like the slope, calculating slope. You can memorize that for 0, first, and second order, but you're not really going to know how to use it until you see it in a practice problem and try to work out the problem. So again, I have this here just to show you guys all the different ways that these can be used and the derivations of the rate law formula. But again, the most important thing is to do the practice problems and use this almost like a reference sheet if you guys need to, okay? Yes.
All the integrated rate laws in the first order halftime are on the like your equations.
Oh, perfect. Then even better. Yeah. More of a reason not to memorize it. Okay. Okay. Now, before we move on, I do want to bring up one thing about 0, first, and second order. Okay, and this you guys might want to write down just so that you guys can not memorize it, but just so that you guys can keep it in mind. Okay, if you have a 0 order reaction, okay, what that means is that the rate is not affected by reactant concentration. Okay, that's the key thing about 0 order. And we talked about that a bit earlier because there was a question. But if you have a 0 order reaction, those are reactions where it doesn't matter how much reactant you have, it's not going to change the rate. Okay, so like when you're screaming at your parents to buy you something, but they're not affected at all, right? It doesn't affect the speed at which they buy it for you. That is a 0 order reaction. Okay, yeah. Yeah, so the rate law is just going to be right here. It's only going to be affected by the constant. If you look at the reaction, rate is only equal to the K value. It is not affected by how much of the reactants you have. Yeah. So they'll usually give it to you, or they'll tell you, or you'll look at the chart and you'll see, like the chart we just saw, and you'll see, oh, the rate's not affected even though I'm changing the concentration. So that's how you would identify it. Yeah. Yeah. So yeah, so you'll be doubling these values, but the numbers here won't change. That's how you can identify it. Yeah, good question. Okay, first order reaction. Okay, easy way to think about first order reactions is that the rate moves linearly with the reactant concentration. Okay, basically, if you double the reactant concentration, the rate doubles. If you triple it, it'll triple. Quadruple it, it'll quadruple. It just moves in a linear fashion. Okay. Okay, and then anything beyond that is going to be, so I'm going to do 2+ order reaction because it could apply to third order as well. The rate moves exponentially. with the reactant concentration. Okay. So this is where, you know, in math, you guys always wonder, why do I need to know how to graph x squared, right? But this is where it kind of matters, because if you graph x squared, right, at 1, it's going to be 1. At 2, it's going to be 4. That's basically what a second order reaction will be. As you go further along, and then it'll go up to 9. So as you increase the concentration, the rate will go up exponentially with that. Okay. So this is where we use this graphing stuff. Okay. Sorry, I didn't know if you were doing sign language or. Okay, make sense, guys? Okay. Yeah, like I said, this is my least favorite unit because it's so abstract and math heavy. Yeah. So technically kinetics, there's a section where you need to know calculus to do it. So when you go to college and if you do chem, you'll have to use calculus for kinetics. But in AP chemistry, we only do the algebra section. If you know calculus, though, it does help in certain areas, especially the graphing. Yeah. Yeah, but you don't need to know how to use it. They're all, you can solve all of them algebraically, but there are some questions, like, especially if you guys notice, there's linear equations. If you can integrate those lines, if you guys know what that means, you're able to do things a little bit easier if you're familiar with the calculus. But if you don't know calculus, that's okay. You can still solve all these algebraically. Okay. And I got a little summary here if you guys missed any of that or if you guys want more clarification. All right, last new information. Okay, you guys might have learned about half-life in your bio classes, whatever. Yeah, apes. Okay, it's not the video game, but half-life is basically the amount of time it takes for the concentration of a reaction to go down by half. Okay, so easy way to think about this is, you guys know I love coffee and caffeine goes inside my body, right? Okay, let's say this is Mr. O, okay? Okay, and he's sad. Okay, because, oh no, he's happy because he drank coffee. Very happy. Okay? And then, so let's say inside my body, there are 10 milligrams of caffeine, okay? Because I just drank my coffee. It's amazing. Okay? Now, the amount of time it takes for the caffeine levels in my body to go down by half, so to 5 milligrams, okay? And so here, Mr. O is getting a little bit less happy, okay? That is called the half-life, and we can write that as T1/2, okay? So that half-life, that T1/2 represents half-life. It's the amount of time it takes for half that caffeine in my body to disappear, okay? And you can use this in any other circumstance either. The amount of time it takes for half of the reactant concentration to be halved, that is called a half-life, okay? And then the next half-life, the second half-life, is going to be when this concentration right here goes down by half, so 2.5 milligrams. Okay, that's another half-life. And at this point, Mr. O is getting sad. And he's shrinking too. Okay, but that's another half-life. Yeah, I'm shrinking too. Yeah, basically, as I get older. And then another half-life is when it goes to 1.25. So the point that I'm trying to make is that it's not 10 to 5 to 0. It's 10 to 5, and then half it again, 2.5, half it again, 1.25. That's what a half-life is. Yeah, so theoretically, it'll never reach 0, but it will get to the point where it's extremely close to 0 so that it's negligible, that difference. Yeah. I'll always be caffeinated to some degree. It is indeed. But at 1.25, I'm just mad. Yeah. And I'm just ahead at that point, yes. Okay, that's not why I'm short, okay? Okay, it's my genetics. You look at my family, and I'm like, dude, I was destined to be short. It's a miracle that I'm my height right now. Okay, come from a family of fat midgets. Basically hobbits, dude. I'm a hobbit. Alright. And then they expect me to play basketball against these 6'3" guys. Anyway, that's my rant. Okay, so let's go to 11-11. So we're gonna get into some practice problems now. Any questions on Half-Life? All right, cool. Okay, now I need a coffee. Okay, so while I make a coffee, I want you guys to do 11-11. Okay, I want you guys to take a look at A, B, C, and D, and I want you guys to use your knowledge about the rate law to figure out which one of these can represent K for something that is third order. Third order, I know. Okay, so one of these is the unit of measurement for K for a third order reaction. Okay, I want you guys to figure out which one of these can represent third order, or just write it down. Yeah. Okay, guys. So out of these four, which one is the one that represents a third order reaction? 3. Yeah, C is the one that represents a third order reaction. Nice. Okay, now you should have noticed that rate law again. This is the rate law. Easiest way to do this is just to put it at the power of 3, because that's the easiest way to get third order, right? If you wanted to do one where you have multiple, right? If you want to be extra like that and do this, you could, but at the end of the day, the unit of measurement is just going to be the same, so 3. Okay, so we can rearrange the equation. Rate on top, concentration on the bottom to the power of 3. You guys know that rate is molarity per second, and then it'll be molarity third. So this cancels out one of them, gets it to 2. And then so you have molarity to the power of -2, seconds to the power of -1. Now we can rearrange seconds, right? We can change up seconds to be minutes or days or millennia, whatever you want. It just has to be a measurement of time. And so that's why it's C. Okay? Yes.
So exponents matter.
Yes, exponents matter. Exponents the thing that matters the most. Everything else from there is changeable. Yeah. Alrighty, let's move on to the next one. Okay. Ooh, okay, I'll give you guys 3 minutes to try this one. I made that noise because this is, I'd say, pretty difficult. You'll refer back to the chart that we looked at. But I want you guys to figure out which one of these line points corresponds to a first order reaction. Okay, so you're gonna need to use that table. The table will definitely help. Okay, anyone want to take a shot at which one it is?
D.
Yes, it is D. Easiest way to think about it is first order is the only one with a natural log. Okay, so if you got a natural log of the concentration, that's gonna be first order. Okay, first order. Okay, so just keep that in mind. Okay, if you have a natural log, it's gonna be first order. So that's the first part. The other option is B. Whoa, I drew that line way too long. Okay, so it could either be B or D. But if you guys take a look at the chart, it'll tell you that the slope is -K. Okay, so first order is gonna be natural log and -K. So yeah, these are some of the questions that might be on the AP test. And if you're familiar with graphing the natural log equation, then it should make sense. But if not, I recommend just memorizing that part, okay? And then Robbie, you said these integrated rate laws are on your thing, right?
No, yeah.
Okay, yeah, so that should help us.
The like rate one.
Yeah.
Has the outline.
All right, let's go on to the next one, 11.13. Now this one is gonna require you to do some maths. So I will give you guys about 5 minutes to try this one, and then we'll go over it. Okay, guys. So for this one, we want to start off by identifying our variables. So I always recommend writing down the variables and labeling them just so we know what's up. Okay. Okay, so it says the initial concentration of a reactant in a zero order reaction. Now the first thing we need to write down is that this is a zero order reaction. Okay. And that is going to mean that the rate is independent of the concentration of the reactant. Okay, so its rate is just equal to K. All right. It tells us the initial concentration. So I'll put a initial is going to equal 0.75 molarity. Okay, and then the K value is going to be 0.015 molarity per minute. All right, so far so good. Okay, so we have the rate constant and the rate, we have the rate law as well because we know it's a zero order reaction. Now all we got to do is figure out the concentration after 15 minutes. Okay, now we know that the K is going to be 0.015 molarity every minute. So every minute, that means that the reactant concentration is going to decrease by 0.015 molarity. Okay, and it's going to be constant. Okay, so pretty simple from here. All you got to do is take your K value and multiply it by the time that's going to elapse, which is going to be 15 minutes. Okay, minutes cancel out. And then you just need to multiply that by 15. And that's going to give you how much the molarity is going to decrease. 0.015 times 15. That means your molarity is going to decrease by 0.225 molarity total. Okay, so this is how much it decreases. So from there, you just take your initial, which is 0.75 molarity. You're going to subtract 0.225 molarity. And that is going to give you your final answer. So 0.75 minus 0.225. And so the final concentration will be 0.525 molarity. And that is going to be your final concentration. Okay. Okay, so far so good. All right. Let's go to part B. Okay, so part B, it gives you a different value. It's going to give you the final concentration this time. The final concentration is going to be 0.06 molarity. So this time we're working backwards. We have the final, and we need to find the length of time it takes to get here. Okay. All right, so first we want to figure out the change in the concentration, right? We want to figure out how much the concentration changed. Pretty easy from there. All we got to do is subtract final minus initial. So 0.06 minus 0.75. So that means that the concentration changed, it decreased by 0.69 molarity. So far, so good. Okay, from there, pretty easy. We just need to calculate. We just need to use some dimensional analysis, right? I want to get rid of molarity, and I want to find time, right, which is in minutes. We know that the rate is going to be 0.015 molarity per minute. So we just need to divide, and then we're all done. And we're going to divide by 0.015. That means that it took 46 minutes. That's it. So if you guys notice, a lot of this is just basic algebraic manipulation. So just make sure you're pretty comfortable using your algebra to manipulate these numbers and these units of measure. That's pretty much it. Alrighty, you guys chilling? Alrighty, cool.